Hey everybody, welcome back to another Whiteboard Wednesday. I'm super psyched for today. We're talking about the pathogenesis of Hashimoto's, or in other words, how it develops and understanding the big players involved in this disease. If you've ever wondered the science behind this and how it develops, then this is the video for you. There's a lot of material. I'm going to try to get through it as much as I can in a short amount of time, but it's probably going to be a little bit longer than normal, so I hope you enjoy this. So thyroid autoimmune disease, like Hashimoto's, is one of the most common diseases that we know of in the autoimmune category. And it affects roughly 8% of the US population. Now, it begins where people have evidence, if they were to test it, but they don't, evidence of antibodies in their blood, anti-TG, anti-TPO, but they don't have any symptoms, or they might have slight symptoms known as the prodromal period. But eventually, you end up into subclinical hypothyroidism territory where you have a high TSH, probably a normal T4 and T3. And then antibodies start to creep up higher and higher and higher over the years, and you might have symptoms that magnify, right? And most people end up with a diagnosis in full-blown Hashimoto's stage 3. And that's where you have high predictive antibodies like TPO and TG, you have a lower TSH, you have a lower T4 and T3 as well. You might have goiter, you have significant symptoms, and there's severe destruction of the thyroid. Probably like 70 to 90% of the thyroid is destroyed. All right, so quick note here on antibodies, because a lot of people get fanatical about their antibody levels, and we need to maybe change our perspective a bit. I'll tell you why. It's important for diagnosing Hashimoto's, okay? We just mentioned that, right? They show up many, many years prior to a diagnosis, but there is very, little evidence that I know of that antibodies have a predominant role in the pathogenesis of the disease. The amount of emphasis we place on antibodies in retesting every 4, 5, 6 weeks, whatever, and crossing our fingers, hoping that they go down, just creates more undue punishment, distress, and anguish, only worsening the inflammation anyway, when in truth they will fluctuate throughout your life, likely depending on what you come across throughout your lifetime and when you decide to test your antibodies again. Antibodies are an indication that there is a command being sent to other parts of the immune system, but it may not correlate with a high immune attack. Antibodies aren't doing the damage. And just because antibodies go down and everyone rejoices and celebrates, while it's not a bad thing, it doesn't guarantee that your thyroid is spared. As long as symptoms are there, low antibodies doesn't help much. You really want both. And the reality, and we're going to get into this in a little bit, is that the tissue destruction comes from other parts of the immune system, like the T cells, the CD8 cytotoxic cells, your macrophages, and cytokines. So let's quickly go through a background on the immune system, because it'll help you when I describe its role in Hashimoto's. So we have like two sides of it. We have the innate side, okay? And then we have the adaptive side. And the innate side is where you have, your natural killer cells, you have your macrophages, you have your dendritic cells. And basically, these three guys right here are known as, they have the role of an antigen presenting cell, and they are essentially doing something that's really important in Hashimoto's, which we'll come back to. But on the adaptive side, we have where the base of the T cells come from, right? T cells, B cells. T cells are of particular importance because of their role in autoimmunity, but particularly Hashimoto's in this case, right? Because they have the ability to differentiate or subdivide, if you will, into other versions of T cells. So after T cells migrate from the bone marrow into the thymus, they mature into these CD4 plus T cells. And when they interact with antigen presenting cells, which I'll come back to, upon activation, they subdivide into things you may have heard before, like Th1, right? Th2, Th17, and T regulatory cells. Okay? In Hashimoto's, we find a predominance of Th1 and Th17, and a drop or suppression of T regulatory cells. This largely all comes from genetic variations triggered by a certain antigen or pathogen or something, which I will elucidate a little bit later. So to give you a quick summary of these guys, right, Th1 cells are mainly involved in tissue damaging reactions. They stimulate macrophages in the innate immunity side that we spoke about. And they also stimulate B cells, which make your antibodies. And this is where you can have delayed hypersensitivity reactions, right? It's what a lot of functional med doctors do, right, when they want to test for antibodies against food, right? You may have heard of an ALCAT or an IgG test of some sort. So that is essentially what's happening, but the reaction is so delayed that you can have symptoms many days or even weeks later. But anyway, that's the difference between a IgG response versus an IgE allergy response, which comes from your B cells that make antibodies too, but Th2 cells are able to stimulate B cells, which turn into plasma cells and make these IgE antibodies, which you've done this, you measure them, and we do that for allergies. Because if there is a low dose allergen, for example, like pollen or eggs or shellfish, it gets presented by a dendritic cell, for example, and activates these mast cells you may have heard of, and thus you have what are known as eosinophils, in case you want to know that. They basically release these granulocytes and histamine and all these things that make you have itchiness, sneezing, congestion, watery eyes, and so forth. Th17 cells have a central role in autoimmune diseases because they respond to infectious agents and they also really maintain the autoimmune condition. They secrete this damaging cytokine, interleukin 17, and that's a problem in Hashimoto's. Now, gut dysbiosis, overgrowth of certain bugs, high salt intake actually can contribute to high levels of Th17, and also they stimulate macrophages, the antigen-presenting cells that we talked about here. And the final thing I want you to remember in this system is the CD8 T cell that's derived from the immature T cells. And basically they are like straight assassins that will destroy anything that they see. And which subtype displays is determined ultimately by the type of antigen, whether it's a metal, an environmental toxin, a pathogen, virus, whatever, its concentration, the nature of the antigen cell presentation, and any genetic influences that are involved, which they are. So here's how that looks. When you have something like a virus or a metal or a food, these antigen-presenting cells, called phagocytes as well, macrophage or dendritic cell, they are basically like consuming this thing, this food, for example, and there it is, right? They then chop it up, right, into fragments, and then that fragment is combined with a protein that it makes, and this whole complex here moves upwards towards the cell membrane. So then you have this, thing sitting on the surface of the membrane that contains the protein that it made and the fragments of that food, for example. And this two-piece unit is what is known as an HLA class 2. And antigen-presenting cells, like macrophages, are the only ones that can make these proteins. So this then triggers T cells. And they come and bind to this, well, it's over here, but they come and bind to it, and this whole cascade happens, which I'll get into. But before we get into this T cell cascade and the thyroid destruction that ensues, let's go through briefly some of the genes that are involved here with Hashimoto's that influence the immune system's behavior, and we'll talk about some other genes that do other things. So there are different genetic SNPs, or single nucleotide polymorphisms, or genetic variations, if you will, that are found in autoimmunity, and particularly in Hashimoto's. And we found a few key ones that we can discuss here. We just spoke about the HLA class proteins, right? And these are proteins that are actually encoded by genes called MHC genes, or major histocompatibility complex genes, that are found on chromosome 6, in case you want to know that. So when we're talking about one of the causes for an abnormal immune system, it's variations in this MHC encoding for HLA proteins that cause for different T cell binding affinities. Okay, so T cells are binding to things that probably shouldn't be happening, and causing this reaction that shouldn't be happening as well, versus somebody who had a normal or wild type set of genes where they don't have that, right? People who don't have autoimmune disease, for example. So some of the genetic variations that we find this happening with is HLA, DR3, there's DR4, and there's like DR5, I think. And, just so you know as well, there are class 1 proteins too. And, so maybe you've heard in celiac disease, for example, that we are going to test, these certain genes to see if you have a predisposition for celiac disease. Some of the genes you may have heard about when we're testing in the context of celiac disease are HLA DQ2 and DQ8, and they are referencing these HLA class 1 proteins. So in Hashimoto's, there are certain genetic variations we found that could show up for some people, and that's DQA1 and DQB1, so you know. And ultimately, one of the things that can happen is this molecular mimicry phenomenon where T cells bind to the antigen-presenting cell, and that protein that it's binding to looks a lot like your thyroid, and therefore it cross-reacts and attacks that thing, and then your thyroid. Other than the HLA genes, we have other SNPs like CTLA4, okay? And this has been studied a lot in autoimmunity, but basically it codes for the protein CTLA4, and this protein hangs out on your T cell membrane. So basically when a T cell binds to an antigen-presenting cell and its receptor, this protein is released and helps inhibit T cell proliferation into these other T cell subsets like Th1, Th17, right, those problematic ones. And we found that there are genetic, SNPs of this gene in Hashimoto's, resulting in an inability or reduced expression and function of this protein, and that's a problem. This has also been found in Graves' disease and type 1 diabetes. Now, real quickly, thyroid-specific genes that we found with more evidence include things like thyroglobulin. All right, so this is a gene that makes thyroglobulin, and it's an easy target for the immune system. Also, TPO, potentially, right? Genes associated with programming cell death, apoptosis. That's also been found. This one, SEL1L, okay, that's a gene that makes some proteins, and we have VDR, vitamin D receptor. Now, let me tell you about this one. This is actually a really, really important one. Many immune cells express this receptor, dendritic cells specifically. And this is important because when vitamin D binds to it, it promotes T regulatory cell development, right? T reg cells are the ones that put the brakes on the immune system. And one of the reasons why vitamin D status in the body is so important in autoimmunity is because some people have SNPs in this gene, so they don't make the receptor work properly, and they therefore don't bind to vitamin D quite so well. So therefore, they don't benefit from T regulatory cell stimulation. However, there are other ways that you can upregulate T reg cells beyond vitamin D, like glutathione and zinc and pine bark, things like that. But it's actually really, really important. So aside from these guys, there are a couple other ones that I'll quickly mention. You can have issues with the gene that actually is involved with producing T regulatory cells, okay? Even production of some cytokines that or proteins rather, that inhibit cytokines. And then overall, though, it's CTL1 that we found. It's thyroglobulin and HLA SNPs that are the most important ones to remember when it comes to Hashimoto's. So Hashimoto's and thyroid damage arises from a loss of self-tolerance from the immune system, which stems from these genetic predispositions, which we just spoke about, and subsequently you have this aberrant immune response. But something has to set it off, right? There has to be something to initiate it. We often hear about, in functional med, right, the triad here. You have the genetic side of it, you have the environmental trigger, and you have a leaky gut. Genetics account for like 30% of it. It's not that, right? It's your environment, your lifestyle, and everything else that basically causes your autoimmune disease. Okay, so some stimulus has to initiate the autoimmune cascade. So things like chemicals, polyaromatic hydrocarbons, polyhalogenated biphenyls, PPA, food, gluten, dairy, viruses, mold, Lyme disease, Epstein-Barr, right, cytomegalovirus. Heavy metals, they can cause modification of your own self tissue and that can cause an immune response. And then you have things like estrogen, which is predominantly in females, right? And that can stimulate B cells. And so that's why females are at a huge disadvantage, and most autoimmune diseases like Hashimoto's is a female problem. Okay, so I want to talk about the postpartum period real quickly, because a lot of people have questions about this and wonder why they have Hashimoto's right after pregnancy, and they have no clue why. Or they had it previously, before pregnancy, and they feel amazing during the pregnancy, and then they get out of it and they get it back again, and they're like entirely confused. During pregnancy, your T regulatory cells are increased. So you have your B cells and your T cells that just drop. And that's intentional because your body is really smart. Why would it want to make antibodies to attack potentially your fetus, right? That's what's happening. So there's an overall suppression of Hashimoto's. If you had it before you got pregnant, that's why you feel great. And then if you don't have it before you got pregnant, you can develop it because there's a huge swing from Th2 to Th1. But nonetheless, in the postpartum period, there is a decrease in T regulatory cells. So it does the opposite once you get out of pregnancy, and you reestablish this immune response, which leads to Hashimoto's. And actually, studies show that there's an increase in TPO antibodies as soon as like 6 weeks after delivery, and they hit peak level around 20 weeks after delivery. Okay, just wanted you to understand that. So let's talk about the pathways of the immune system and how this thyroid destruction happens. So we have the genetic side of it that we talked about. We have the trigger of some sort, multiple triggers, never really just one thing, multiple antigens, which cause a loss of immune tolerance. And in truth, full-blown Hashimoto's stems from many, many years of this interplay between a dysfunctional immune system and an antigen of some kind. The development of thyroid destruction must begin with antigen presentation from an MHC2 class protein. So, you have dendritic cells. They mostly make these MHC2 class proteins. So after they bind to something like, BPA, for example, they accumulate in the thyroid, right? So you have the dendritic cell here, and you have your BPA, okay? Now, then this entire thing moves out of the thyroid, and you have, the BPA and your dendritic cell, and they move into the lymph node, right? And like a neighboring lymph node, okay? They migrate there, and now, strangely enough, what you'll find, and I didn't know this for a while actually, is that your thyrocytes, right, your thyroid cells, essentially, they can become antigen-presenting cells themselves. They can showcase parts of your thyroid tissue to your T cells, right, independent from this. Pretty crazy, right? But nonetheless, this entire complex moves into the lymph node, where we find antigen-presenting cells, T cells, antibodies from the B cells, and the antigen-presenting cells present this antigen to the autoreactive T cell, right? So here's the T cell. It's connecting to that complex right there. And all of a sudden, this autoreactive T cell gets triggered and starts to stimulate your B cells that make antibodies. And then you have antibody production being made. These T cells subdivide into Th1 and Th2 17 cells, which cause a lot of havoc, as you know. Now we have what's known as clonal expansion and maturation of these autoreactive T cells and B cells. So they basically travel back, right? Back into the thyroid, B cell and T cell. They travel back to the thyroid along with CD8 cytotoxic cells. Remember I mentioned that before, CD8 cells, and macrophages, for M for short. And they come join the party. The naive T cells we spoke about before differentiate into Th1 cells most of the time, and then they release certain cytokines like interleukin 1, interleukin 12, interferon gamma, TNF alpha, which signal more of these macrophages. They're antigen presenting cells too, remember? So they can again do this whole thing about picking up BPA or gluten or something, and this entire phenomenon starts over again. So as long as Th1 is active, this can be active too. So macrophages are doing their thing, going out there, picking up more things out in the body. CD8 cells are doing their damage, and then B cells are flagging the thyrocytes, your thyroid cells. And then that recruits more T cells and more macrophages and more CD8 cells. And that's how you get this damage. And it goes on and on and on and on. They release cytokines. And ultimately, macrophages are releasing cytokines as well, too. And they're making a lot of free radicals. And then you actually have the complement system of the different area of the immune system, which we didn't talk about, but that's activated too. So collectively, all of these immune cells cause apoptosis, which I'm sure you've heard of before, which is this like collapse of these cells and they die, right? So through this antibody-dependent, cytokine-mediated, and free radical-mediated process that causes cell death. So that's essentially how it happens. I want to talk lastly about one quick thing, right? So iodine is one of these things that a lot of people talk about. They supplement with it, but there are dangers with it. Yes, it's important. We need it for thyroid hormone production. But I would say going over 200 micrograms per day is probably not advisable. And that includes supplement form and even intake of iodine-rich foods like kelp and seaweed and spirulina and things like that. The issues with iodine is that while, like I said, it's a substrate for thyroid hormone production, it can create too much hydrogen peroxide. That's a free radical that will do more of what we just talked about, right? Cause more damage. And you really need, glutathione or selenium to balance it out. That's why you should supplement with those things too, probably. And then lastly, like I said before, salt can easily be an issue and a problem in increased Th17 cells and the cytokine, which is involved in Hashimoto's. So I would probably say stay in the lower end of the sodium intake. The RDA is like, 2,300 milligrams or something like that. So maybe somewhere in the thousands. And, that wouldn't be a bad idea. All right, so that's it. Thank you so much for paying attention, and I hope you enjoyed it. I know it's probably a lot of information, and some things went over your head, but I'm sorry, but not really. So anyway, catch you next time for another Whiteboard Wednesday. Take care.